In this lecture, we will provide the precise definition of a stabilizable system and then present a very nice test for checking stabilizability. We already talked in an informal way about a stabilizable system, which was, roughly speaking, such that if you can make all the solutions converge to the origin of a system by choosing a proper and appropriate input signal, then that system is said to be stabilizable. Okay, so therefore, if a system is controllable, it's naturally or it's immediately stabilizable. But even uncontrollable systems sometimes may be stabilizable. Okay, and when that is the case, that's what we will be talking about in this hour. Okay, now as before, we will make use of controllable decomposition when studying stabilizability. So consider the system. Okay, x that equals ax plus bu and y equals cx plus du. Okay, this is our, let's say, the initial or the original system with the following dimensions: x is in Rn, u is in Rk, and y is in Rm. Okay, well, stabilizability has to do with the pair AB only, but for the sake of generality, let's put down the entire system, both input and output. Now, we know that from previous lectures, this system has a so-called controllable decomposition. Okay, with controllable decomposition. Okay, Z, C, Z, U. Okay, so this together is our new state Z in our new representation, and we partition the state to ZC and ZU. C for controllable, U for uncontrollable part, in a sense. Okay, so this vector dot equals the A matrix or the A tilde or A bar matrix plus the new B matrix, okay, B bar matrix, U. Here we have ZC, ZU. Now, the new A matrix has the following structure: AC, A1, 2, 0, and AU. It's upper block triangular. And the new B matrix has the following special structure: BC and 0, where ZC is in Rn bar and ZU is in Rn minus n bar, where n bar is the dimension of the controllable subspace of this system. Okay, and similarly we can write for the output plus du. This part is called CC, this part is called CU, and here we once again have ZC and ZU. Excuse me. Now we will introduce the precise definition of a stabilizable system through the controllable decomposition. So let's do that. Okay, so let's call this system, or this representation 2. Now, system 1, the original system, is said to be stabilizable if either n equals n bar. Remember that n bar is the dimension of the controllable subspace if it equals n. So that means controllable subspace is the entire space Rn, which means that the system is controllable. So system 1 is said to be stabilizable if either it's controllable. Okay, in that case, the matrix AU will be non-existent. Okay, AU non-existent. Okay, we won't have such an input. Or when AU, if exists, is a stability matrix. Okay, that is, all the eigenvalues of the matrix AU are with strictly negative real parts. That is, the real part of the eigenvalues of the AU are strictly negative for all eigenvalues lambda I. Okay. This definition has a very natural discrete time version. Okay. So system 1 is said to be stabilizable. Everything is the same until the last part. Even the last part can be taken to be the same if AU is a stability matrix in the discrete time sense, which would mean that all the eigenvalues are with magnitude strictly less than 1. Okay. Okay. So let's try to convince ourselves that if system is stabilizable according to that definition, then all the solutions can be made converge to 0 for this original system. So this is not really a proof, but just an informal demonstration, okay, informal argument. First of all, note that ZU dot equals AU ZU. Okay, so there's no way that we can affect this ZU dynamics either directly through the input, because this is 0, or indirectly through ZC dynamics, because this entry is also 0. So ZU dot equals AU ZU. So ZU dynamics depends only on the initial ZU conditions. Okay. So that implies if the system is stabilizable, that is, if AU satisfies that condition, that all the part of the state that we call ZU will converge to 0 exponentially as t goes to infinity, provided that if AU is a stability matrix. Okay. All the eigenvalues are with significative real parts. Then let's look at the ZC dynamics. Okay, ZC dot. Then what we have is ZC dot equals AC ZC plus A12 ZU plus BCU. Okay, ZC dot equals AC ZC plus A12 ZU plus BCU. Now, if AU is exponentially stable, then ZU is converging to 0. Therefore, this term will become more and more insignificant. Okay, so this term decays exponentially. So it's reasonable to assume that after a while ZC dynamics will be approximately B AC ZC plus BCU. Okay, and then we know that because this is controllable decomposition, we know that the pair AC-BC or this system is controllable. Therefore, we can always find an input and make ZC converge to 0. Okay. Now, let's continue our argument. The pair, excuse me, the pair AC BC is controllable, okay, because we're taking them from the controllable decomposition. Therefore, ZCT can be made converge to 0 as time goes to infinity by some proper choice of control input U of t. So what we have is ZC of t going to 0, Z of t going to 0. Therefore, the Z state considered as a whole is converging to 0. Okay. Then ZCT, ZUT can be made, therefore, to converge to 0 as t goes to infinity. Okay. Now, we know that system 2 is obtained from system 1 through a similarity transformation. Therefore, system 1 and system 2, they are algebraically equivalent. System 1 and system 2 are algebraically equivalent. That means x of t can be obtained from z of t by some similarity transformation matrix T. Okay, ZCT, ZUT. Okay, this is an n by n matrix. Okay, as a result, since this matrix is constant and this z of t is converging to 0, therefore the x of t, the state of the original system, must be converging to 0. Okay. As a result, x of t, the state of the original system, can be made to converge to 0. Okay. In other words, if system 1 is stabilizable, okay, then, and it turns out then, and only then, it's a necessary and sufficient condition, we can always make by some proper choice of input the state converge to 0 as t goes to infinity. Okay. Now, this definition also produces or suggests a way to check stabilizability given some system, obtain the controllable decomposition, and we have figured out the details of that procedure. So we know how to obtain the controllable decomposition. Once you have the controllable decomposition, pick the AU matrix, okay, and then check its eigenvalues. If all the eigenvalues are stable, okay, that is with strictly negative real parts for a continuous time system, or all with magnitude strictly less than 1 for a discrete time system, then your system is stabilizable. Okay. So that's one way, but there are some other very nice and sometimes more useful ways too. So today we're going to talk about one of those methods, namely the eigenvector test for stabilizability. Basically, it's a very nice extension of the PBH test. that we developed for checking the controllability of a system. Okay. Here is a nice check for stabilizability. Okay. It's called eigenvector test for stabilizability. Okay, so consider the system x that equals ax plus bu with x is in Rn, so it's an nth order system, and the size of the input vector is, let's say, k. Okay, this is our system 1. Now here is the eigenvector test. System 1 is stabilizable if and only if no eigenvector of A transpose with the corresponding eigenvalue that's unstable, that is, the real part is 0 or positive, lies in the null space of B transpose. Okay, so system 1 is stabilizable if and only if, here is the statement, no eigenvector of A transpose with eigenvalue real part of lambda is 0 or positive, that is, with eigenvalue on the closed right half plane, belongs to the null space of B transpose. Null space of B transpose. Okay, so let's call this statement the eigenvector test statement E. And this theorem has a very nice discrete time version, which reads that no eigenvector of A transpose with eigenvalue magnitude equals to 1 or larger belongs to the null space of B transpose. Okay, so remember that this is very similar in structure to the controllability test that we have talked about earlier, namely the PBH test, okay, which was a system is controllable if no eigenvector of A transpose, okay, we skip this part, belongs to the null space of B transpose. Okay, and now for stabilizability, it's okay that certain eigenvectors of A transpose belong to the null space of B transpose, but as long as no such eigenvector with the eigenvalue satisfying that condition belongs to B transpose, then null space of B transpose, then we're safe. The system is stabilizable. Okay, let's construct the proof. So let T be the similarity transformation. Okay, that will take us to the controllable decomposition. B transformation that puts our system 1 into the controllable decomposition representation, okay, where the A matrix, the new A matrix, let's call it A bar, reads AC A1, 2, 0, AU, which is related to A through that product T inverse AT, and the new B matrix, let's call it B bar, which has the following form that we're familiar with, BC0, and that's related to the original B matrix through the following identity. Okay, B bar equals T inverse times B. Okay, now to show the equivalence, because it's an if and only if condition, what we're going to do is we're going to first show that stabilizability implies this statement E, and then we will talk about the reverse direction. So let's start with the first part. Okay, now we will show that if the system is stabilizable, then the statement E must hold. Okay, so to show this, we will use one of our favorite proof methods, namely contradiction. Okay, so we say that we suppose otherwise. Okay, that is, we will start with a system that's stabilizable, but this condition doesn't hold, and then we're going to see that that leads to a contradiction. Okay, so that is the system 1, okay, it's here, is stabilizable, but there exists an eigenvector. Okay, so by definition it's non-zero, and the corresponding eigenvalue C, which is unstable with, well, in the sense that it's on the closed right half plane, the real part is 0 or positive, such that A transpose V equals lambda V, and that V belongs to the null space of the B transpose. Okay. So once again, we're supposing that system 1 is stabilizable, that is, the eigenvalues of the matrix AU are all with strictly negative real parts, but so that holds. Also, what holds is we have an eigenvector of A transpose whose eigenvalue is unstable in this sense, and it's in the null space of B transpose. Okay, now we're going to show through a contradiction that these two things together cannot coexist. Okay, so what we have is the following: A bar equals T inverse A T. Okay, so we start with that. So that implies T A bar multiplying both sides with T. Okay, from left we have T A bar equals A T, and then take the transpose of both sides. We have A bar transpose T transpose equals T transpose A transpose. Okay, now there's here a little funny thing about the notation. This T is a transposition T, and this T is our matrix T. Okay, just keep in mind T, and then we can now write the following: A bar transpose times T transpose equals T transpose A transpose, and so this equation we multiply both sides with this eigenvector V. Okay, V, and that equals what? A transpose V is lambda V. Okay, so here we have T transpose lambda V, and lambda is a scalar. We can put it anywhere we like, and we can write this as lambda T transpose V. Okay, so what we have obtained is A bar transpose times T transpose V equals lambda times T transpose V. Now, since V is non-zero because it's an eigenvector, and T is non-singular, therefore its transpose is also non-singular, T transpose V is a non-zero vector. So, and that vector satisfies A bar transpose T transpose V equals lambda times T transpose V. Therefore, that vector is an eigenvector of A bar transpose. Okay, so let's call this equation 2. Now, define or give this vector a name, T transpose V. Okay, define W as T transpose V. Okay, this is our non-zero vector W, and let's partition W as W sub U and, W sub C and W sub U. C and WU. Okay, and now let's try to figure out the implications of this identity that we obtain. Remember that A bar has this form. Okay, now starting from the equation that we obtained here, 2, which says that W is an eigenvector of A bar transpose, and the corresponding eigenvalue satisfies this. Okay, its real part is 0 or positive. Now from 2 we can write the following: A bar transpose W equals lambda W. Okay, so let's write A bar transpose as this matrix transpose. So that implies, if you transpose this matrix, what you have is AC transpose, okay, 0 transpose, A12 transpose, and here we have AU transpose. Okay, so that's our A bar transpose times W, which is WC WU, and equals lambda times W, lambda WC, lambda WU. Okay, so we're going to use it later on. Therefore, let me call this equation star. Now, this implies what? This implies that, okay, just look at the first row, AC transpose WC plus 0 equals lambda WC. Therefore, AC transpose WC equals lambda WC. Okay, so that looks like an eigenvector equation. Lambda WC. What else? Okay, let's call this equation 3. What else? We have also the following: B transpose V equals 0. It's here, okay, by assumption. So that implies B transpose times, let's write V in terms of W. V is T transpose inverse times W. So what we have is T inverse transpose times W equals 0. Okay, and that can be written as T inverse times B transpose times W equals 0. Okay, because this thing can be written as T inverse times B, and then you take the transpose of the whole thing. Okay, and finally, that means, because this was B bar, okay, T inverse times B was B bar, that means B bar transpose times W equals 0. Now let's remember the shape of B bar. B bar was BC and 0. So B bar transpose is BC transpose times 0 times W, which we partition as WCWU, WCWU, and this equals 0. So that means BC transpose times WC equals 0. BC transpose WC equals 0. So let's give this a number, equation 4. So let's look at equations 3 and 4 at the same time. So here we have a vector that seems to satisfy the eigenvector equation for AC transpose, and that vector is in the null space of BC transpose. Okay. Now, the eigenvector test for controllability says that if a pair is controllable, AB, then no eigenvector of A transpose can belong to the null space of B transpose. Okay. Now, since these matrices AC and BC, they come from the controllable decomposition, and we know from an earlier theorem that that pair, because we're talking about controllable decomposition, that pair AC BC is controllable. Okay. Now, if the pair AC BC is controllable, then W of C cannot be an eigenvector. Okay, because if it's an eigenvector, if it satisfies that equation, well, it satisfies that equation, but if it satisfies this equation and it's an eigenvector, then the pair AC-BC would be uncontrollable, which is not possible because they come from the controllable decomposition. Hence, W of C cannot be an eigenvector. And there's only one way for a vector to satisfy this equation and not be an eigenvector, and that's that W of C is the zero vector, because by definition an eigenvector is non-zero. So let's write that down. Since the pair AC BC is controllable, three and 4 implies that that vector WC must be 0. And that implies what? Now W of C is 0 and V is non-zero because it's an eigenvector. Therefore W is non-zero because this is a non-singular matrix. So W is non-zero and W of C is 0. Therefore this part, the WU component, must be a non-zero vector. W of U must be different than 0. Okay, now W of C equals 0 and W of U different than 0. We will now, in the light of this new discovery, we will now revisit equation star. So let's do that. Then equation star produces what? Okay, let's look at the second row. This guy times W of C. W of C is 0, hence we can ignore that. Plus this guy times W of U equals lambda W of U. Okay, so we have AU transpose W of U equals lambda W of U. Okay, now W of U is a non-zero vector, therefore it's an eigenvector of AU transpose. Therefore lambda is an eigenvalue of AU transpose. Therefore lambda is an eigenvalue of AU, because a matrix and its transpose, they have the same eigenvalues. So AU has an eigenvalue lambda, and that eigenvalue is with non-negative real part. So that means AU cannot be a stability matrix, and as a result the system cannot be stabilizable. But that's a contradiction to our very first assumption. Okay, lambda is an eigenvalue of AU. Okay, and because the system is stabilizable, we have to have that all the eigenvalues of AU are with strictly negative real parts. Okay, so what we have obtained is this and this must hold simultaneously, which clearly is a contradiction. Okay, therefore, this has been shown. If a system is stabilizable, then it must be that the eigenvector test is, or the eigenvector test condition is satisfied. Okay, now we're going to show the reverse direction. Okay, if the eigenvector test condition holds, then the system must be stabilizable. Implies stabilizability. Again, let's try to do it by contradiction. Suppose not. That is, this holds the condition of eigenvector test, but system is not stabilizable. Okay, and let's see what that implies. That is, E holds, but system is not stabilizable. Therefore, the matrix AU in controlled decomposition has an eigenvalue with 0 or positive real part. Lambda satisfying real part is 0 or positive. Okay, then we can find a non-zero vector xu that's in Cn minus n bar, and n minus n bar is such that AU is an n minus n bar by n minus n bar matrix. So this is of appropriate size to be multiplied by this matrix AU, such that AU transpose XU equals lambda XU. Okay. Now AU has an eigenvalue satisfying that, and that eigenvalue we're calling it lambda. Since AU and AU transpose, they share the same eigenvalues. Therefore, AU transpose also has an eigenvalue satisfying this. And by XU, we're denoting the eigenvector corresponding to that eigenvalue of AU transpose. Okay. Let's see the consequences of this. Then we can proceed as follows. Okay. We can write A bar transpose times 0 XU equals, okay, so A bar transpose is here. We have AC transpose A12 transpose 0 AU transpose times 0 XU. Okay, that equals, for the upper part we have AC transpose times 0 plus 0 times XU, therefore the upper part is 0. As for the bottom part, it's this matrix times 0 plus AU transpose times XU. AU transpose times XU. Now AU transpose times XU is lambda XU. Therefore, this we can write as lambda times 0 XU. Okay. So what we have shown is that this matrix, this vector, 0 XU vector, is an eigenvector of A bar transpose. Okay, so that's our equation 1. Furthermore, B bar transpose times 0 XU equals BC transpose 0. So that's our B bar transpose. times 0xu, and that produces this times 0 plus 0 times xu, so that equals 0. So that's our equation 2. So what we have figured out is that A bar transpose has an eigenvector with the eigenvalue satisfying that, and that eigenvector belongs to the null space of B bar transpose. Now if we can transfer this information to a similar kind of information for the pair AB, then we will have shown what we desire to show. Let's do that. Okay, so for that, what we do is we define this vector that we call z, and that z we construct from this eigenvector, 0xu eigenvector. Okay, that's defined as T inverse transpose times 0xu. This is a non-singular matrix, and xu is non-zero, therefore this is a non-zero vector, therefore z is a non-zero vector. Okay. So we will now show that z is an eigenvector for A transpose, and the eigenvalue, the corresponding eigenvalue is lambda. Furthermore, that z belongs to the null space of B transpose. Okay, if we can show that, we will have shown that this statement is violated, and we will have the contradiction that we wanted. Okay, so A transpose Z equals T A bar T inverse transpose Z. Okay, so this is how we can write A, and then we're transposing it. T was our similarity transformation. So that equals T inverse transpose A bar transpose, and then we have T transpose times Z, and that equals T inverse transpose. Okay, now Z is defined as such. If you multiply both sides with T transpose, what you have is T transpose Z equals 0xu. So T transpose Z, okay, equals 0xu. So what we have is A bar transpose times 0xu. Okay. Now A bar transpose times 0xu is lambda 0xu. Okay. So therefore that equals T inverse transpose times lambda 0xu, okay, where we used equation 1, which says that A bar transpose times this vector equals lambda times the same vector. And then this equals what? Okay, T inverse transpose times 0xu is Z, and this lambda is scalar. We can carry it anywhere we want. So what we have obtained is this equals lambda times Z. Okay, lambda times Z. Let's call this equation 3. That is A transpose Z equals lambda Z. So therefore Z is an eigenvector of A transpose, and the corresponding eigenvalue is on the closed right half plane. Furthermore, B transpose Z equals T B bar transpose times Z. That's B bar transpose times T transpose times Z. Okay, and T transpose Z is 0xu. B bar transpose times 0 xu, and b bar transpose times 0 xu is 0. Okay, therefore b transpose z equals 0. And what we used is, we used equation 2. And let's call this equation 4. Okay, and now what remains is just to write the concluding sentence. Since real part of lambda, okay, is greater than or equal to 0, 3 and 4 clearly contradicts the statement of the eigenvector test. That is, we have an eigenvector z of A transpose whose eigenvalue satisfies this, and also it belongs to the null space of B transpose. Okay, therefore E, the statement of E cannot hold, hence we have the contradiction. Okay, now before we end this lecture, let's make the following very simple observation. Through which we can rewrite the theorem. It looks like a different theorem, but basically the statements are the same. Okay, so the theorem we have just proven can also be written as follows. Note that we can restate the eigenvector test for stabilizability as follows. And when it's done in this way, it's sometimes called the PBH test for stabilizability. Okay, PBH, Popov, Belevich, Hutus. Okay, so they are the initials of the inventors of this test for stabilizability. Okay, the system x dot equals ax plus bu, where the order of the system is n. Okay, x is in Rn, is stabilizable if and only if this rank condition is satisfied. A minus lambda I B equals n, and the order of the system. Okay, if this condition is satisfied for all complex numbers, for all scalars lambda, then we know that the system is controllable. Now, the version of the test for stabilizability does not require that this is satisfied for all lambda, but for lambda only with non-negative real parts. Okay, so if this holds for all lambda on the complex plane satisfying this, then the system is stabilizable. Okay, this is actually nothing new here. It's just a restatement of the eigenvector test. Okay, if you look closely, you will immediately see that.